Hey man, what happened? I'm in area 0, you're in area 1. I thought we were gonna become neighbors.
I don't know, man. That's just how my owner configured me.
Well, if you're in area 1 and I'm in area 0, we can't be neighbors.
Hello and welcome back to the next lesson in the OSPF for CCNP and Beyond course. If you don't know already, this video is part of a complete course on OSPF that should cover everything you need to know for the CCNA, CCNP ENCOR or Advanced Routing and Services exams, so on and so forth. Please give a like and subscribe if you're enjoying the content so far, as that'll help me keep creating more. You know what time it is? Let's see what we're learning today. In the last lesson, we talked a bit about the OSPF Router ID. First, we'll revisit that and go a little bit deeper. Then we'll talk about OSPF neighbors, the neighbor states, and the requirements for establishing adjacency or becoming neighbors in an OSPF domain. The OSPF Router ID. So we know the OSPF Router ID is a 32-bit number uniquely identifying an OSPF router. The router ID must be unique for each OSPF router in an OSPF domain, and it must be unique between OSPF processes on a router. A router can run more than one instance of OSPF, so in that case, each OSPF process needs a unique router ID. The router ID is chosen in one of three ways. You can manually configure it using the router ID command under an OSPF process, but if you don't manually configure the router ID, it will be chosen first based on the highest active loopback IP. If there are no loopbacks, it will use the highest active interface IP that you have configured. The router ID is used as a tiebreaker in the designated router and backup designated router elections, but we will cover that in more detail when we explain the DR and the BDR in the next video lesson. OSPF neighbors are routers that share a common network link with OSPF enabled on their interfaces. So OSPF routers discover other OSPF routers via the hello packet. An adjacent neighbor is an OSPF neighbor that shares a fully synchronized link state database. A router only becomes truly fully adjacent with the designated router and the backup designated router on a segment. Again, more on this later. If I had $1 for every time I've said that so far, I could buy a pair of AirPods or something. But moving on, the OSPF state machine maintains a table of adjacent OSPF neighbors and the states of those neighbors. Let's see the table of neighbor states on the following slide. These are the different neighbor states for OSPF. You can find this table anywhere online or pause and take your own notes. From the time you enable OSPF on an interface and start to discover neighbors, the router will move through these states before becoming fully adjacent. Without getting too far ahead, some routers will stop at the two-way state. I guess I'll just crack the nut here. Not all routers in an OSPF domain become fully adjacent with all other routers. In the next video, we explain why and what, but for now, I'll just say that the routers only become fully adjacent with the designated router and the backup designated router to save resources and conserve on routing traffic. Moving on, the down state means that no hello has been received for any neighbor. Manually configured OSPF neighbors will always be in the neighbor table, so you might see a manually configured neighbor in a down state. One example I can think of when you would have a manually configured neighbor is a hub and spoke type topology like DMVPN. You would see manually configured neighbors there, and if a link was down between any two of them, you might see a neighbor in a down state. A router may also be down if there hasn't been a hello within the dead interval. Routers in this state will either resolve and move to higher states or be deleted from the neighbor table, which is known as being forgotten. Attempt is something you will only see again with manually configured neighbors for non-broadcast multi-access network types. We'll discuss network types in a future video, so don't really worry about this phase for now. Init is the stage where we have received a hello from an OSPF neighbor, but that neighbor has not acknowledged our own hello packets yet. The two-way stage means that I have received a hello from my neighbor and they have received a hello from me. We are able to tell this thanks to the neighbors field of the hello packet. When we see our own router ID and the hello packet from the neighbor, we know that they have received our hello packet and we now have bidirectional or two-way communication. The next phase is the XStart phase. This is the first step in becoming adjacent and the start of the link state database exchange. Also worth mentioning here is that in between these two phases, in between the two-way and the XStart, This is where the designated router and the backup designated router election takes place. You already know what I'm going to say. We'll cover that more in the next video. I'm going to start doing 10 push-ups every time I say that phrase, and I'll be ripped by the end of the course. But back to the xstart phase. At this point, the routers form a dominant and subdominant relationship. The dominant router has the higher router ID. The dominant router chooses the starting sequence number for the database description packet and LSA exchange. After xstart, we move to the exchange state. At this point, the local link state database is sent in database description packets. The DBD sequence numbers are used for reliable acknowledgements or retransmissions. Next, during the loading phase, we send link state request packets to ask for more information about LSAs the local router does not know about, and we receive the link state updates. After this is complete, we reach the full state where the neighbors are fully adjacent, which means they have synchronized link state databases. It's important to know these states because sometimes a router might become stuck in a phase and you need to troubleshoot that. For instance, routers can become stuck in xstart or exchange state due to the MTU not matching on both sides of the link. For example, if you configure a GRE tunnel and form OSPF neighborship over that tunnel, one side might have been configured for a different MTU than the other, and you would see this problem. So when you see the neighbors in a certain state, it's helpful to have some knowledge about what happens in that state so you can troubleshoot. There's a great Cisco document on troubleshooting adjacency, which I'll link to in the description. I would definitely check that out. I want to go over the requirements for adjacency on the next slides, and then we'll get into the lab and do some configuration and basic troubleshooting or common misconfigurations. OSPF adjacency requirements. Here they are. First, we have the interface area ID. Remember the intro in this video where I said me and the Hound couldn't become neighbors because we were in different areas? This is what I was getting at. The interfaces in question must be in the same area to form an adjacency, otherwise you'll run into problems. The hello and dead intervals must also match. In EIGRP, the K values have to match, and OSPF, the timers have to match. The interfaces have to be on the same subnet. So the network address has to match, in other words. I think different versions of Cisco code might behave in different ways, but the masks don't strictly have to match. As long as the network mask on one side includes the IP address on the other side, you can form a neighborship. So a /30 on one side and a /24 on the other, for example. This is obviously not recommended practice anywhere. It's just an interesting technicality. Just because it works doesn't mean it should ever be done, but I've seen some practice test questions where they try to throw you off with this. So they'll say, what's wrong with this neighborship? And they'll show you 2 masks that are wrong, and that's actually not the answer. Try this out on your own lab gear of choice and let me know what you find out in the comments. The interface MTU also has to match. I mentioned before that routers can be stuck in xstart or exchange phase if the MTU is mismatched. It's recommended to change the MTU and some other things when you have GRE or IPsec configured due to increased header sizes. If this is not configured the same on both sides of a tunnel where you are using the tunnel to form OSPF neighborship, you might see this problem. The network type must be compatible. The network type doesn't have to strictly match. Some network types elect a designated router and backup designated router, and other network types do not. This is what I mean when I say network types must be compatible but do not have to match. I'm about to do 10 push-ups because yes, we are going to explain exactly this point, network types, designated routers. We're going to explain it all in the next videos. Now, excuse me while I go do my push-ups. Moving on, our authentication also has to be correct. Finally, the routers must agree on stub flags, and here comes 10 more push-ups because I'm going to explain stub areas in a later video. You definitely want to stick around for that part because stub areas really confuse me, but they're actually pretty simple and we're going to go all in on that. So definitely stick around for those videos. Now, what we're going to do is have a lab session. I highly suggest you lab along with me if you can. Pull this video up later and try to repeat it, something, because watching is great and it's always a great place to start, but if you really want to hammer this stuff in your brain and reinforce your learning, the best way is lab. So if I'm lucky, we'll get out of the lab session and I'll only owe you 50 push-ups. See you at the command line. All right, so welcome to the lab. What we have here is the simple topology you see on the left-hand side. The IP address for each router is 10.1.1.x, where x is the number of the router, so .1, .2, .3, .4. We're going to configure all of these routers to be in area 0. We're going to manually configure the router ID on 2. We'll have the loopback selected on the 3rd, and we'll have the IP selected on the 4th to show all the ways the router ID can be selected. We'll use network statements on 2 routers to enable OSPF. Then we'll use interface statements on the other routers. We'll show the adjacency coming up, possibly do a packet capture at the same time, run through some show commands, and then we'll break it, and then we'll close the video. So let's get started. I've already done the IP addresses on the routers. So we'll go to CompT. We'll do router OSPF. I'm going to use 1. The number doesn't really matter. It's locally significant. And in this case, we are going to assign a router ID. The reason it couldn't allocate a router ID is because I don't have a interface up right now. I don't have a loopback and I don't have an interface up. So we saw that message because a router needs a router ID to participate in OSPF. And because we don't have an up interface, it wasn't able to select one, but we just configured one, so no worries. Now I'm going to use a network statement, but what I'm going to do is use the all zeros, and this is a wildcard mask. So what I'm saying is enable OSPF on every interface, and we're going to put that in area 0. So if I do show IP OSPF interface brief, we can see that E00 is participating in OSPF. If I had other interfaces on this router, they would also be participating. I just only have one plugged in right now. So that's a way you can enable for every interface on the router. Moving on to router 2. In this one, I'm going to do router OSPF 2. The rest I'm going to use 1 just so it's easy to remember, but I just want to show you that it is locally significant. Doesn't have to match in EIGRP. The autonomous system number has to match. In OSPF, the process ID does not. So router OSPF 2. Again, no up interface, so we can't get a router ID. We're going to manually assign that. Router ID 2.2.2.2. Now we're going to use network statement to enable 0, 0, 0. Again, the wildcard mask, area 0. Now, any interface that has an address in that network should be participating in OSPF. So do show IP OSPF interface brief. And we can see that 01 is in fact participating. This command shows us the interface, the process ID of OSPF, the area, the address and the mask, the cost, the state, how many neighbors. Moving on to router 3. In router 3, I need to configure a loopback interface first. So we'll do interface loopback, then we'll do IP 3.3.3.3. Now that we have that, we can start the OSPF configuration. What I'm going to do in this router is enable OSPF at the interface level. So we'll go into interface E02. We'll do IP OSPF 1, area 0. Now, if we do show IP OSPF interface brief, we can see that 02 is participating. So that's the difference between the network statement and the interface configuration way of enabling OSPF. Now, if we do show IP OSPF 1, we can see that the router ID was selected as 3.3.3.3. I didn't configure that, but because I have a loopback, this was selected. Now, on router 4, I am going to no shut the interface where I have the IP. Do show IP interface brief. So we can see that the IP of the up interface is 10.1.1.4. Again, we'll do router OSPF 1. Now, if I do show IP OSPF 1, we can see that the ID selected was in fact that interface IP. Again, we'll go into interface E03, we'll do IP OSPF 1, area 0. And we can see that interface is now participating in OSPF. Now, on this particular router, what I'm going to do is turn on debugging view. I'm also going to start a capture on that interface. So right now, the only router that has the interface up is router 4. What I'm going to start doing is I am going to no shut the interfaces on the other routers as quick as I can. Then we'll hop back on router 4 and we'll watch the adjacencies come up. So 0, 1, no shut, no shut, no shut. And we can see we already have some output, and we have the full adjacency here. Still getting some updates and acknowledgements here. Again, there's 4 neighbors on this segment, so this might take a little bit. If we do show IP OSPF neighbors, what do we see? Okay, we have full states with everyone, so I'm going to stop this capture and we'll go over that. So what we see going on here, what we see here is the wait ending. I've told you about the hello interval and the dead interval. There's another interval called the wait timer, which, yes, I'm about to do 10 push-ups because I'll explain it in the next video. Next, what we see is that DR BDR election. We've elected the backup designated router, the designated router, DR BDR none. Without adjusting the priority, again covered in the next video, but without adjusting the priority, the router with the highest router ID is going to win. So that's why this one was selected as the designated router. You can see we have database descriptions. This is coming from router 1. We've got two-way communication to router 1, which means that in our hello packet, we saw our own router ID from the hello packet sent from router 1. Now we were able to elect the backup designated router. We've got DBDs coming through. Now we're in two-way with router 3. Now we've elected the router 3 as the backup designated router because it has a higher router ID than router 1. Sending database descriptions to router 3. Again, we're just going through some of the DR and BDR stuff. Two-way communication. Now we have two-way to router 2. So again, remember that means that in the hello packets, we see our own router ID and the hello from router 2. Router 2 agrees on the currently elected DR and BDRs. Again, database descriptions. In here, you can see that we have LS updates going out, LS acknowledgements, and basically, long story short, this process continues until you become fully adjacent. Now, what I want to show you is if I do show IP OSPF neighbors, we can see that we have 3 neighbors on this segment, which makes sense because if we're router 4, we have these other 3 routers and we're on the same network segment where OSPF is enabled on all these interfaces. Because router 4 turned out to be the designated router, we have a full state with every other router. I almost don't want to say it, but I'm going to explain it further in the next video. But remember, I told you some routers will stop at the two-way state. If we look at router 1 and router 2, they're DR others because they're not the backup designated router and they're not the designated router. Again, not adjusting the priority, the designated router is going to be elected based on the highest router ID. So the designated router is router 4 because it has the highest, and the backup is going to be router 3 because it's the next highest. So that's why we see router 1 and router 2 as other routers. Now, if we go to router 1 and do show IP OSPF neighbors, we can see that we are in the two-way state with router 2. We have a full adjacency with the backup designated router and the designated router, but we're in the two-way state with router 2. This is expected and nothing to be alarmed about. You also see in the neighbors command that you have the dead time. So if we keep going, these are counting down, and this one just reset because the dead time is 40. Now we'll just run over some show commands. So one is show IP OSPF neighbor. This will show you all the neighbors you have on the segment and the state that you have with these routers. Because this says full with every router and this one is BDR, we can tell that this is the designated router. There's other ways to tell that, but you can also tell it from this output here. This interface is the interface that you're establishing the neighborship over, and this is going to be the IP address of the neighbor. This is the router ID of the neighbor. Now, if we show IP OSPF interface brief, so that full command is show IP OSPF interface brief. We can see here all the interfaces that we have participating in OSPF. Because there's only one here, we see that it's Ethernet 03, which makes sense. You have the process ID. If we go back to router 2, I believe it was, to show IP OSPF, we can see the process ID here is 2. So yes, they don't have to match, or no, they don't have to match, I should say. We have the area that you're in on that interface, the IP address and mask, the cost, how many neighbors you have, so on. Now, if we show IP OSPF interface, this is going to give us a detailed list of all the interfaces. Because we only have one here, there's only one, but you can get a lot of information from this command. If you look here, you can see the timers. So it's 10, 40, 40 for hello, dead, and wait. We see that The hello is due in 3 seconds, so it keeps track of when it's expecting to receive hellos from the neighbors. We've got our neighbor count here. The adjacent neighbor count is 3. If we look at interface, if we look from here, we see the adjacent neighbor count is only 2 because, as I mentioned, the routers only become fully adjacent with the DR and the VDR. Going back to router 4, you can find the cost of the interface. We'll go over that soon. You see the router ID here. You see your area, your IP address. You're attached via an interface statement. If we go back here, we can see this is attached via a network statement, so we can see how OSPF is enabled on the interface, whether it's via network or via interface statement. And another important thing here is the network type. So you can also see the network type. There's a lot of other commands here. I suggest getting in the lab and seeing what some of these are, but we'll just show IP OSPF 1. So this is just going to give you some basic information about the OSPF process. You have the process and the process ID. You have your router ID, when it started, how long it's been up. And you've got some other information here. You've got information about your area, how many interfaces you have in that area, the authentication, and so on. Another one you can use is show IP protocols. This will show you all the routing protocols you have enabled. So again, you can find the router ID here, things like that. Another interesting one is show run. Then we can type SRO. So in this case, because we didn't have any network statements, we just have the process enabled. But if we go back here and we do show run, type SRO, and what that stands for is section router OSPF. Then we can see we've got a manually configured router ID. We've got the network statement. If we show it here, we show run. Again, you can just see the configuration of OSPF, quick and easy. That might help you. Now we'll break a few things and see what happens. Let's say on router 4, we go under OSPF and we want to configure the router ID. We're going to take router 1's router ID. When you make this change, you have to clear the IP OSPF process or reload the device for it to take effect. Do yes. Now we should see some errors. And as you can see here, because we have the same ID here as here, we get the error message on screen. So in order to fix this, we're going to have to, again, configure the router ID. I'll change this for now to 4.4.4.4. Do clear IP OSPF process. Yes. Debug. And again, we can see some of this exchange going on. So again, we're going through some of these election processes. We're exchanging our LSAs and we're becoming synchronized. So that's fine. Now, what I'll do is if we go into interface E03, what if we have an area mismatch? So let's say we do no, take that off. Now we'll do IP OSPF 1, area 1. And we should get some errors here. So we see here that we received an invalid packet, mismatched area ID from backbone area from router 3, now from router 1. So all these routers in their hello packets are saying, hey, I'm in area 0. Router 4 is saying, hey, I'm in area 1. They don't want to become neighbors with each other. Here we can see that 40 seconds went by from the time we took down router 4. So it purged that from the table. So neighbors. Nothing's going to come up there because we can't establish neighborship. Neighbors. Here we don't have 4 as a neighbor. So what we'll do is do show run and E03, no. We'll put that back in area 0. And again, we have our neighborships. Something worth mentioning, again, we'll go over it further in the next video on DR and VDR, but even though we have the highest router ID, we're still not becoming the designated router. There's no preemption in this election. If 2 routers elect themselves as DR and VDR for a segment, and then a router with a higher router ID comes online, it will not elect itself DR or VDR until one of those other routers goes down. Again, next video. What's that? 30 push-ups? We'll see. Okay, so what I did was I just made a tunnel interface between 3 and 4 because I can't change the MTU on the physical interface in this lab. So what I'm going to do is make an OSPF neighborship over the tunnel that I just made. The only thing I need to do this for is to show you the MTU mismatch. So I'm going to do a new OSPF process on these routers. OSPF 4. We're going to use a network statement, and that's going to be 4.4.0. 0. So the only neighbor we have here is there. Okay. Perfect. Now, if I go into my tunnel interface and MTU, we'll just change this to 500, doesn't really matter. So we'll change the MTU on one of the tunnel interfaces. Now, do show IP neighbors. Need to wait some time. Clear the IP OSPF process. So we need to clear the IP OSPF for this to take place. We lost our neighborship. So you can see we're in the Xstart phase. And we're not going anywhere. So if we look at router 3 here, we are in the exchange phase. But we're still in Xstart here, still in exchange here. So as you can see, we have a problem. If we do show run int turn 0, if we take out this MTU size, you can see that we instantly go into a full state there. So I have shown you an area mismatch and MTU mismatch, as well as duplicate router ID. Those are some common problems you can have when configuring basic OSPF. And if you rerun through this video, you have everything you need to configure some basic single area OSPF. So in this lab, the main things I wanted to show you was the basic commands to get OSPF up and running. Also wanted to give you a sneak peek into the fact that some routers stop at the two-way state and only become fully adjacent with the designated router and the backup designated router. And I showed you the different ways you can configure the router IDs as well as enabling OSPF either on an interface directly or via a network statement. So I hope this has been informative. Let's switch back over to the presentation and wrap this video up. All right, so in this video, we covered the router ID and how it is selected or configured. We also went over the OSPF neighbor states and the OSPF adjacency requirements. We just got finished a lab session with basic single area OSPF configuration and some troubleshooting or misconfigurations. I did a bunch of push-ups behind the scene and now I'm super strong. One thing I would suggest you to do is to turn something like that up in your own lab. One thing we didn't do was change the timers for a router and see that error. So set yourself up some basic OSPF, find some more show commands you can use, break it, fix it, just mess around with it and run the commands yourself, because that's really going to help you and it's going to get you up to speed for the next sessions that we're going to do. In the next video, we'll finally cover those two guys, the designated and backup designated router. I'm excited to meet them because they have caused me a lot of push-ups. We'll also cover the election process for the DR and the BDR. If this video has been helpful, make sure to like and subscribe for more trainings. And as always, thank you for watching, and I hope this is helping someone. Make sure to turn up your own lab because that's really the best way to learn. Let me know how your lab is going for you in the comments, and until next time, see you then.